So you can get this new model from our website at www.cityLabs.com/tutorials.html, which is a new page that we put up to house the demo model. It's no longer distributed with the software installation. You just go to our website to download and install it. And the model catalog can be downloaded from the section titled Demo Models. And then we have a tutorial as well that accompanies this demo model and provides some additional background and sort of step-by-step processes for actually running the CubeTown activity-based model, as well as some of the same information presented here in a slightly different form about the background behind the activity-based model. So the application structure in CubeTown looks like this when you open the application. Basically, this is just a expression of the steps in the activity-based model. We, of course, have GIS output step as well, and we have pilot steps that automate the process of starting and stopping cluster nodes based upon the number of processors available on the local machine. Although you could also distribute processing across a network using kubecluster, which is a nice feature not possible with multi-threading, by the way. And so, this is also kind of an example of using kubecluster to automate this kind of record-based processing. One thing to mention here is that we just run one iteration, but in the original implementation, there was a feedback loop with the congested output from assignment going back into the initial accessibility and activity travel simulator. And I think it'd be fair to say, Mark, that most actual implementations would include that feedback loop, correct? It's sort of necessary in order to ensure consistency.
Yeah, definitely.
Yeah. So we wouldn't encourage you to go out and implement this as is without a feedback loop. You would have to incorporate some kind of feedback loop in order to have a valid activity-based model. Okay, so just some of the scripting techniques. One is the use of DBI. Record-based processing was used in the first version of the activity-based model, and that just kind of marches through a record table, almost like a spreadsheet in row order, from row 1 to row whatever to the end of the file. Whereas DBI records are not automatically read. It allows you to jump around and non-linearly read or randomly read from a record file using the DBI readnext and DBI read record functions. This is a description of these functions. Both of these functions will return 1 if the request is invalid. And by the way, we provide detailed training on all of this at the Advanced Scripting course, which we'll be offering coming up very soon now, 2 weeks from now in Atlanta. If you're interested in learning more about using DBI and seeing some detailed examples with hands-on use of DBI for this kind of work, certainly go check out our training website to find out more about that training course in Atlanta. So both of these functions will return 1 if the request is invalid or outside the range, so you can test to see whether you've made a valid request for a record. And the DBI readnext can also take a negative number to search backwards in the file. And again, this didn't exist at the time the original implementation of the activity-based model was done in Voyager. So we found that this really helps out when we're processing these record tables in the activity-based model. We can get any field value using the variable di.number.name, where number is a file number. We can have up to 10 of these DBI files, whereas in record processing, just one rec.i file was available. So we can actually do relational database processing. You can also get the total number of data records. And you have special arrays dimensioned as the number of fields, which allow you to actually extract variables without knowing their name or heading on the file. So in the activity-based model, for example, in the population synthesizer, as well as the activity-based model, we have some value lookup using the DBI seek function, which is an example of using DBI files somewhat like lookup files, except that you can actually do multi-value lookup. So if you sort the records in a DBI file, the sort fields represent an index or cardinal key in database terminology that can be searched, and then you can match against some or all of the sort fields in order. And this is a function called using DBI seek. The first argument is the DBI file number, 1 through 10, and then the other arguments are values to search for in sort fields. So on the right here is an example of exactly how this works in the activity-based model example. And the main use of this here in this particular case is to process DBI records by zone, which allows us to cluster the processing, whereas, again, with the older RecI or record-based implementation, it was not possible to cluster the processing for the activity-based model.
Well, you could do it. You'd have to.
Oh, yeah. Go ahead.
So you could do it like brute force just by creating separate population files for different ranges of zones and then run separate instances, but
yeah. I guess
this makes it a lot more elegant.
There are always multiple ways to skin a cat, aren't there? You know, I think the other thing is that actually DBI is just a little bit faster on its own, even if you didn't use cluster. And I'll get to that in a second, but there's a runtime reduction factor actually just from switching to RecI to DBI for just straightforward, even just going linearly through a table without any clustering or anything like that. So there are also a lot of lookup functions used in the activity-based model. These were in the previous implementation. They're in the same implementation. We're distributing with KubeTown. Obviously, a lookup table can be used anywhere in Voyager script. These are used in the tour generation component of the activity-based model to identify the tour structure, the number of stops before and after, the number of sub and secondary tours, the secondary tour type, time of day. And Mark, aren't these sort of really where the parameters of the model are input? Really, if you wanted to customize this model, these would be the lookup tables that you would modify in order to, sort of customize the model for your area. Is that fair to say?
Well, these particular ones are sort of the structure of the model, what the alternatives are, and which alternatives correspond to other alternatives or constrain other alternatives. But I suppose you could, depending on how you want to program it, you could use lookup tables for a lot of things, for model coefficients and for other types of things.
Yeah, you're right. I take it back. This is more about the model structure. It's true. But anyways, yeah, there's a lot of stuff that's nicely put into lookup tables here. So also make use of something that has been around for a while called Mattfile, which is a way to read an input matrix within a record processing program. It's random access of matrix values rather than sort of linear access by iZone marching through the list of zones. And this is used in the mode destination choice model. This Mattfile function has 5 arguments. The first is the Mattfile number, then you have the table number, and then you can index by INJ and just sort of randomly access matrix values. And if you're using this, sometimes it could be a little memory intensive because the rows are cached in order to enable this random access. So you can increase cache size on computers with larger memory availability to improve the speed, or decrease to reduce the memory requirements. So there's always kind of a trade-off between speed and memory here. But this is one thing you could play with if you were trying to improve performance on modern machines.
Yeah, I would say in general, with activity-based models, the more memory you can have, the better. I mean, memory is fairly cheap, and the best is if you could just store all your matrices right in core all the time, because they're not. If you don't have thousands of zones, that should be possible on most machines where you have a couple gigs of memory, and because activity-based models don't really work with where you model all the travel going from one zone to every other zone and then from the next zone to every other zone. Because you have tours, and the tours can have non-home-based trips in them, so it doesn't follow that same sort of matrix structure that a 4-step model does.
Yeah, and another comment about cluster here is that if you network a bunch of computers together, even if they each have a limit of 2 gigabytes, which really there's no reason to if you have 64-bit and so forth, but and our code is, Voyager is not optimized for 64-bit, but it will run on 64-bit operating system. So you can certainly access higher, memory amounts with Cube Voyager by doing 64-bit. And The other thing about that then is that if you network using cluster across multiple computers, as opposed to, say, just buying a really big server, which is usually more expensive than getting a bunch of, say, 4-core machines and networking together, and you're also limiting the amount of memory required for each processing node, if you will, right? So you actually can access more memory that way than by just buying one really big machine. So it's another kind of nice, sort of consequence of using the clustering or distributed computing-based approach with Cube Voyager, and that's just a benefit that happens naturally if you're using cluster. Especially networked across machines. It makes it easier to accumulate large amounts of processing power and memory. So about these performance improvements. Well, one thing, just switching to DBI instead of RecI chops about 20% to 30% off the runtime. This runtime reduction factor here is the factor you would apply to the initial runtime in the old implementation, basically. So the reason we didn't put this out there at the beginning is it didn't seem practical at the time for most people, unless they had pretty small models like CubeTown. Even CubeTown takes a while to run. But just using DBI takes 20 to 30% off this runtime. So that's an interesting implementation note, that just the improvements in the script for DBI make this run faster. Then if we start getting into cluster, we really start to see some significant improvements. I mean, almost everybody is running at least a dual-core machine these days for their modeling. And if we have cluster and we use 2 cores versus just 1, we can almost chop the runtime in half. Is a little bit more than half runtime reduction factor, just because the proportion you reduce kind of depends upon the structure of the model and the amount of processing that can actually be distributed, or the efficiency with which it's distributed. And then if you go down to 4 cores versus 1, we can get, again, almost down to a quarter reduction, probably more like 30% to 40% runtime reduction factor. But certainly at that point, we're starting to get into really feasible territory. And again, Cube Voyager, now the standard license of Cube Voyager supports 4 cores. Obviously, you need to buy a separate license if you're getting 8 cores of processing. By the way, if you do upgrade to 8 cores, Cube Cluster comes free. It's called the Cube Professional Upgrade now we're offering. But basically, if you get Cube Cluster and you have 4 cores, this runs in about a third the time it previously would have if you were just using RecI. So with these scripting improvements in place, it's we really felt it was feasible now to kind of put this out there in CubeTown and maybe advocate a little bit for its investigation for potential adaptation or use in certain areas. And performance gains from additional cores beyond 4 will depend upon the structure and size of the population zone system. These runtime reduction factors are just for reference. They're not going to be the same everywhere. But certainly, I mean, if we compare this to the runtime on a typical model per zone or something like that, at this point, it's starting to look like a more favorable comparison relative to the initial comparisons that were done. So, and of course, it's not to say that you can't use cluster or distributed processing with other activity-based models that are in Java or C++ or what have you. There are ways to do that. I think it's just that maybe they're not as easy to follow for a Cube Voyager user, or easy to implement for a Cube Voyager user who doesn't have significant programming experience or expertise. Other things that have been done since then, we didn't have the GIS when this was all first done, so it was nice to be able to tie the outputs into the GeoDatabase and do mapping. For example, here we have a select zone of residence analysis, which is different from the usual select zone analysis, which looks more at sort of origin destination select zone, whereas this is looking at all the trips made by residents of a particular zone. And we can plot, we can extract a matrix of those trips and do a desire line plot of those trips, which is shown here. And it shows trips made by Zone 1 residents between other zones. So if you're thinking about analyzing developments and doing development review or traffic impact analysis, it's a kind of interesting approach that maybe perhaps takes into account the contribution of development-generated trips to traffic in between other zones, not the zone in which the development actually occurs.